Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to a new discussion which we are going to have on various techniques to generate digital elevation models, and this is in three parts. So let's discuss the first one. As you know that digital elevation model can be generated using various techniques, and whatever the known techniques so far, we will be discussing one after another into these three discussions. And most preferred method nowadays is which is based on remote sensing, because ground based technique are really very difficult, and it is very challenging in sense that there are many areas which are inaccessible to humans, and some terrains are very difficult to cover on a vehicle or foot, and therefore the best preferred method nowadays is generating digital elevation models which is based on remote sensing. So whatever the methods which we are going to discuss so far, which are known also in the research domain or in literature, that is the earlier method which we used to have is about using survey toposheets or topographical maps, and basically using from these maps either point heights which are also available or contour lines. And as you know that contour lines are basically polylines made from several nodes and internodes. So using those nodes or node points, we can do the interpolation, spatial interpolation, which are various interpolation techniques which we have discussed under that topic, and where the input is generally is point data, point theme, point vector data. So contours can be converted to point, or nowadays many softwares are capable of converting themselves within the software. So in the background you don't know on the screen, or you can use the point heights or data coming from other sources, maybe GNSS and differential GNSS, that is differential global navigation satellite network data, or the data can come from other sources also. So it does not matter, as long as we are having point heights or contour lines, we can employ spatial interpolation techniques, which are many, and can generate digital elevation models. And second is the first, though here in the this methods it is among second, but among remote sensing method, this is the first technique which was developed, and it started with the spot. Earlier we used to have stereo pairs of aerial photographs, but not stereo pairs acquired by satellites. So this spot, which was a French satellite and launched in 80s, and that has brought a new, I would say paradigm shift in case of generation of digital elevation models employing stereo pairs. So that was the first satellite which started providing stereo pairs, and using then employing photogrammetric techniques, it became possible to generate digital elevation models. Also, as you know that India is having our own satellite like Cartosat, which was really innovative in many sense and designed for this purpose. Why I said innovative? Because Spot used to take from say day 1 with the one different angle, and on day 2 again the same area, whenever there is overpass, the same area used to be covered by a different angle, because for stereo pairs and the basic requirement that the same area should be covered with two different angles, and these angles, if they are same, then photogrammetric techniques can easily generate digital elevation models. So, in Cartoset what it was done, because if there is a, suppose in case of a spot, suppose on day 1 the sky was very clear, on day 2 when it is revisiting the same area with different angle, now you are having clouds. So, the entire pair used to go bad. Whereas in Cartoset the innovation was done that instead of looking sidewise, it started looking forward and backward. So, on the same day, at the same time, almost at the same time, the stereo pair could be generated, and therefore, we can using that data which is about 5 meter resolution. So, that means you can generate digital elevation models of about that resolution without much problem, again employing the photogrammetric technique. So, the advantage of forward and backward looking, that these weather conditions will not change. So, if in one scene there is a cloud, in another scene also it would be a cloud, but if it is clear in one scene, it is highly likely that the another one will also be clear. So, that provided really Cartoset has really provided a great impetus for the development of a digital elevation models. And also if you visit the Bhuvan, BHUVAN, Bhuvan portal of NRSA, which is part of ISRO, you can also download high resolution digital elevation models which has been generated now for entire India, and they are available free of cost also. And then a few years back when we started getting these thermal infrared data, especially from NOAA AVHRR, though NOAA AVHRR sensor provides thermal data at 1 kilometer resolution, but the technique provided the insight that how a digital elevation model can also be generated using thermal infrared data, and especially of hilly terrain, which is most difficult for other techniques, where many techniques may fail for hilly terrains like Himalaya, but this thermal infrared based technique works very well. We will be discussing further on this with some examples. And now the other which has brought really a revolution in case of digital elevation model availability at a global scale was from this SAR interferometry method, or INSAR we say in short, and this is started basically with the SRTM, Shuttle Radar Topographic Mission. That was a mission for about 16 days, and during that time 80% of the globe was covered, and these these radar data pairs were generated, and then SAR interferometry technique was employed, and initially they provided a 90 meter resolution digital elevation model for entire globe except for polar regions. Later on, and later on 30 meter spatial resolution SRTM DM at global scale is also available. But for like countries like America or Canada, they can have even much more higher. But when you go for downloading the data from of SRTM, there are various portals, and during this course also we will be discussing that how from where you can get the data and how you can download the data. So, this when you go for this SRTM data, you may find that instead of writing a 90 meter resolution or 30 meter resolution, they write 3 arc second or 1 arc second respectively. So, 3 arc second roughly equals to 90 meter, and 1 arc second equals to about 30 meter. So, I mentioned this because some people may get confused that I talked here in 90 meter and 30 meter, but on their portals you are finding 3 arc second and 1 arc second. So, it is not 3 meters or it is not 1 meter, it is 3 arc second means 90 meter roughly. Now these radar pairs also later became available from a satellite which is NVSat, which is a European satellite, also Sentinel, which is also a European satellite, and ALOS Pulsar, and one more satellite which started this SAR interferometry also, RadarSat of Canada. So many such satellites, especially in the microwave region of EM spectrum, started providing radar data pairs, and these were employed to generate digital elevation models using this SAR interferometry technique. And definitely resolutions also started improving since then. Now most latest method is based on the LiDAR data, and again it is also a remote sensing method. Earlier the initially development has taken place, which was for the ground based 3D mapping, and later on now the satellites are coming with LiDAR sensors, and they can provide LiDAR data as well. So there are at least 5-6 methods which are available for generating digital elevation models, and which are completely based on the remote sensing. Now we see that first one by one we will start discussing in all these 3 lectures. So the first one is based on the survey topo sheets using contours or point heights and spatial interpolation techniques. So from this perspective I am discussing little bit about spatial interpolation also. As you know that spatial interpolation techniques, basically they turn the raw data into useful information. Raw data here is the point heights, generally it is point heights. So if you see a point height data, you do not get much information, or you cannot have a recognition of a pattern or anomaly or any other such thing. But if you develop a surface using interpolation techniques, then that raw data or point data becomes a very useful information. So this is the advantage of employing interpolation techniques. This becomes a more greater informative content and also value, reveals patterns, trends, anomalies that I have just mentioned. Otherwise, in simple by looking point data, you may miss this. And also it provides a check on human intuition, because it is based on mathematical things. So nothing that one person is perceiving something, another one is not. In this case nothing will, it is a check on human intuition, and where sometimes in the point data where we can miss some anomalies, but here you can really get good details about the data through these surfaces, which is interpolated surfaces. So if we employ a survey topo sheets, like here in this flow chart it is shown, generally these used to be, still they are popular in paper form. So first these have to be scanned. That part I also discussed when we did the georeferencing of a topo sheet. So at that time I mentioned that we have found that through our iteration and experience, that if I have to handle a 50,000 scale topo sheet, and then scanning at 300 dpi dots per inch would be optimum, and there is no need for going 600 dpi or 1200 dpi, because by going for very higher dpi, that may result a very huge file, but no benefits in terms of quality. Because whatever is printed on the paper, if it is in poor quality, no matter how good resolution you are having, sometimes it may not may not bring good results. And also you have seen this part while we discussing georeferencing, because deliberately I did georeferencing on topo sheet. So there will be then link here. So the first you have to do the georeferencing of the topos, scanned topo sheet, that becomes basically your raster, and then you can digitize different features which are present in a topo sheet, maybe for example contour lines, maybe point heights, maybe stream network, drainage network, maybe road network, maybe rail network, and so on. So there are about 8 themes which are presented or printed on a topographic map, and all of them these can be digitized. Now since about a decade, now we have started getting digital topo sheets also in different layers. So for there is a separate layer for contour, there is a separate layer for point heights, there is a separate layer for drainage network. So if digital things are available, then this left side flow, that means this much will not be required at all, and we will have a very good data available, and we can employ these point data or line data or both, and can do the directly the spatial interpolation and can develop a digital elevation model. So it depends in what format you are going to have the data for this kind of generation of DM employing topo sheets. If you are having digital topo sheets, it is really wonderful. This is what we desire. But if it's not, then you have to follow these 4 steps, basically rather 3 steps first, and then you do that one. Also for georeferencing, you can use GPS data to collect the GCPs, ground control points, or maybe using GPS you can update some information on the map if it is required. And then digital elevation models can be generated, which if already digital data is being provided, then of course your interpolation or digital elevation model will have relatively high accuracy compared to manual methods. This is the just example that in the left image what we are seeing, the contour lines which are digitized from topographic maps or topo maps, and you employing these contour lines, we can generate digital elevation models. So from a discrete, from the discrete we get a continuous surface. So and this way we can definitely generate a digital elevation model. When we didn't have these satellite based or remote sensing based techniques for generating digital elevation model, these were the only techniques available for us, and we generated. One example in the previous demonstration I have brought about the this USGS topographic maps. So these USGS topographic maps were also generated employing 250,000 survey topo sheets of almost entire globe. So the contours which were printed on those 250,000 topo sheets were digitized manually, and then some appropriate interpolation techniques were employed, and for entire globe at 1 kilometer resolution, spatial resolution digital elevation model was developed by USGS. So this technique is well established technique. Sometimes when we do not get high resolution digital elevation model for a small area, but we are having at the same time a survey topo sheets, we can definitely use that one and can do the digitization. One more point which I want to mention here, that earlier that for digitization we used to employ hardware which used to be called digitizer. Like for scanning you need a scanner, a big scanner or flatbed scanner or rolling scanner. But for digitization there used to be a digitizer like a big table. And nowadays we do not use those peripherals. What we do now, after this scanning and georeferencing, we can directly digitize on our screen. So the techniques have developed so much that from that manual kind of digitization, now we can go on screen digitization, or also sometimes in literature you will find a little fancy word that is head up or heads up digitization, where you do not look downward, where you look towards the screen. Now as you know that spatial interpolation is the procedure of estimating the values of properties, and properties here when we are discussing digital elevation model are elevations. So value of elevations at unsampled sites within the area covered by existing observations. As you also know that these contours are interpolated from point data. So, in the field, especially while making these survey toposheets, only the point heights is collected, or that data is collected, and then later on the contours are generated. So, contours are interpolated from point data. So, using those information, we can definitely go for spatial interpolation. As you also know, and this we have also discussed while discussing this topic of spatial interpolation, that basically interpolation estimates or predict values for the cell, and of course it is a raster from a limited number of sample data points, because for every location you do not have the observations. So, whatever the observation, whatever the number of points, you can still employ them and in this spatial interpolation, and still you can generate a digital elevation model to some accuracy. And basically it predicts unknown values for any geographic point data, and since your raster is a regular grid, is a continuous, so for each cell there will be a prediction of elevation if elevation values are being used, or some other properties like rainfall, chemical concentration, noise levels, pH, and so on and so forth. Second, as you know that the purpose here or rationale behind spatial interpolation is the observation that points close in a space are more likely to have similar values than points far apart. And this Tobler's law of geography is basically employed extensively in spatial interpolation, and because the point which is very close to observations will have more influence while doing the prediction in spatial interpolation than the point which is very far, or cell which is very far. For example, here I am having just 7 points here, 7 points, and these points are also having some values. Assume that these are elevation values. Implying these points and using spatial interpolation techniques, a surface can be generated like this. So, in between, like for point 16, it has created a cell here 16, and it has also created a cell for 20. Now, but in between we do not have any observation here, but because of interpolation it is filling those values and getting influence of the nearest neighbor, or following the Tobler's law of geography. Similarly, there are now, instead of 7, there are about 60-70 points, and again if the density of points or density of observations is very high, obviously you are going to have a better prediction or better highly accurate digital elevation model. But if you are having just few points as input for a spatial interpolation, the level of confidence in your output may not be as high as in this case. So, one has to remember, if possible, bring as much as observation or bring as much as points possible before interpolation, so that if you are having more observations, it is likely that you will get high accuracy. Now, as you know that digital elevation model is a surface, and a surface is continuous, and what your interpolation is doing, basically it is creating the surface, and therefore understanding about the better understanding about the surfaces is very much required. So, here what we are going to discuss, that each representation or surface representation is useful for a specific situation. What it means, basically, if I am going for Himalayan terrain digital elevation model, then the same technique may not be useful as it is good for plain area like Indo-Gangetic plain. So, we must understand, or we should have a prior information about the area or the ruggedness of the terrain. So, that knowledge will always help us to choose appropriate spatial interpolation technique and different variants of those. Obviously, this is always true for whether you are having plain area like Indo-Gangetic plain or you are having Himalayan terrain. that more observations will always bring better results. So, as also that this digital elevation model is a grid representation, as a surface, it's a raster, and this can be used or considered as a functional surface, because at any given location, for example x and y, it stores only a single attribute or single value, that is z value. So, it cannot store multiple z values. So, you can say that this is the drawback in that sense, but it is not truly, at the end it is not a drawback, because you can still have multiple z values in different layers for the same area, for the same xy location. So, you can have different themes. Suppose I am working, so one surface I am having for elevation or truly a digital elevation model, another surface I am having for groundwater or rainfall, another surface I am having for pH value. No problem. So, that means in each of these layers I will have different z values. So, still I can carry multiple z values, and in an analysis, in any spatial analysis, I can involve multiple layers at a one time. So, there I can, so it is a biomedia by which we can definitely get multiple z values. Otherwise, in a single grid file, you will have only single attribute. If it is a typical digital elevation model, you would have only elevation value as cell value. Now, these functional surfaces are, as you know, continuous surfaces. So, the advantage here is that lot of mathematical techniques which have been developed for these functional surfaces can be directly employed in our domain, that is for analysis and creating new derivatives of digital elevation model. So, in future lectures we will be discussing how various derivatives can be generated using this surface, functional surface, as a digital elevation model. So, as you know that when we talk about typical digital elevation model, then it is basically representing the terrestrial surface or terrain, and that is basically depicting the earth surface, and statistical surfaces that describe demographic, that is also in that sense is a raster and is a functional surface. So, statistical techniques which have been developed there can also be employed in our domain. Mathematical surfaces that are based on arithmetic expressions, those too we can employ, and then this surface representation is the best way to represent the form which is storing x and y z values that define the location of a sample. Because recall, in vector data we can have multiple attributes for each point, each polyline or polygon, but in case of raster for each cell we can have only single attribute. So, that is what we do, that is why it is simple. So, when we have been discussing about comparison between vector and raster, we made a statement or we developed an understanding that raster structure is simpler to understand or to use also as compared to the vector data, because it is in the simplest form. What is that form from mathematical point of view? Is it just two-dimensional matrix. If we are using contour lines representing elevation, then as you know that these lines are drawn using points, and these polylines basically connects those points or equal elevation or iso heights. And generally when we talk about elevation, this point also we discussed in earlier lectures, that it is generally in case of elevation it is measured above mean sea level. Now, there is another surface which we have discussed. So, one surface representation is possible from vector, that is employing contour lines. One surface representation is from raster, that is a typical digital elevation model, and the third type of surface representation is possible employing the tin. Though here it is mentioned vector data surface, but truly it is not. This is neither vector nor raster, but it is quite, in some way it is quite close to vector, So sometimes we also mention that one. Now, as you know that tin is a triangulated irregular surface, and there are a lot of facets which are in form of triangles, and they basically partition the entire terrain of based on observations, our input points x, y and z values. So, these what we find ultimately in a tin is a irregular spaced data points, and these data points are used to create a irregular network of triangles. Now, these points which we use say for the same point data can be used for generating a digital elevation model, a typical raster surface, or the same points can also be used to generate a tin. So, when we will see the demonstration, at that time we will see these two generations of digital, two ways of generating digital elevation models using the same point. And these points in tin basically they connects the edges, and which then forms the contiguous non-overlapping, this is very important, non-overlapping, and create a continuous surface that represents the terrain. So, terrain can also be represented using tin. Now, in raster, as you know that the grid is the spatial data structure which is part of raster, and define space as an array of cells of equal size or square shape, and square shape are arranged in rows and columns, and in case of grid representation each cell contains a single attribute value, and generally in typical digital elevation model that is the z value, and whereas we can also have some other properties also. And the location of these each cell in geographic space can, or in terms of latitude, longitude or easting northing, can be obtained from position relative to grid origin. So, if it is grid is georeference, then you would get the geographic coordinates. If it is still in geometric domain, you would get geometric coordinate. So, generally if you download a digital elevation model, whichever the free digital elevation models which are available from different portals based on different techniques, all of them are nowadays georeference. So, for each point location or each cell location, you not only get the z value, but you also get x and y in terms of latitude, longitude. Now, methods of surface representation in nutshell, a point, point becomes basically input, just looking points, though here it is systematic collection of points, but still it does not give any feeling of the surface or neither pattern or anomalies which are present about a particular property. Whereas contours can give you a feeling of terrain or a surface, but the most appropriate surface representations are through either grid like after interpolations in form of raster or tin, which you see here, which we have just discussed, and that is triangulated irregular network. And this part also we have discussed in length while discussing this spatial interpolation, but since it is we are discussing how to generate digital elevation models employing interpolation, and data is coming from generally from topo sheets. So, for that point of view I will very quickly go through that the visiting as you know that every location on the surface of the earth and collecting the height information is impossible, because there are terrains which are very difficult for humans, and it is not possible to generate a surface for entire globe. So, some techniques have to be employed. So, one technique is wherever it is possible collect the heights, employ the interpolation techniques and generate a surface or predict values for each cell. That is what we are doing in interpolation. Or of course, as you know that interpolation starts with a belief that if you do not have that belief that things are what it is predicting, then the only solution is to go and check in the field if it is possible. If it is not, then you have to rely on some interpolation techniques. Now these input points, in one other previous example we have seen a systematic or regularly spaced points were there. But generally it is not possible in real sense, even if you are using survey topo sheets and you have already digitized these point heights, they would be basically distributed randomly. And if these are not distributed randomly, or if you are not having regularly spaced points, these regularly spaced points are near impossible, and then and if the points are say within one topo sheet, points are only located in one corner, these spot heights, and if you employ that one for a spatial interpolation, you may get very poor results regarding accuracy. So the requirement here when we provide the points, that they should be distributed randomly, not in clustered form, or regularly spaced of course is not possible. So if that is there, then definitely we can create a better digital elevation model rather than using points which are clustered in one corner or in some part of a topo sheet. As you know that interpolation assumes something, and that because it is based on that belief which I have said. So the assumption that makes interpolation a viable option is that spatially distributed objects are spatially correlated or autocorrelated. In other words, that thing which are close, that is the Tobler's law of geography, close together tend to have similar characteristics, and this is what it is exploited in interpolation. So generally, though we say spatial interpolation, but in general it is also a point interpolation, and which is used to create a surface where measurements are not possible. And there might be some issues about the interpolations, the accuracy part. So few times in this discussion I have already mentioned that how accuracy gets influenced by our input data. So if input data is having a high density and input data is distributed in space randomly, you have chosen a correct interpolation technique, you may get a very high accurate digital elevation model. In future lectures, we will also discuss how to check that whether my digital elevation model employing a particular spatial interpolation technique is really accurate. That part can also be checked. Visual representations or visual checking is also possible. Edge effects sometimes because on the boundary area you may not have observations, and therefore it is going for extrapolation, and that may bring again accuracy issues. So these are the some issues or problems with the interpolations. Otherwise it is extensively used to generate digital elevation models employing either point data or polyline data like contours. So with this I end this discussion. Thank you very much.